I'm Mandisha Zhang giving a talk because the students do the work and professor give the talk. But except that, we also have a great collaborator from Cisco. I really enjoyed the talk before me. He said precisely the right word, that is, we want the operators to reduce the number of 3 AM calls. This talk follow exactly that spirit. So what we're going to do is about, we want to do flat dampening without the worry of losing the reachability. So this is old news. Everybody knows that, some time ago, this RFD was introduced. And because there's all kinds of failures, and people wanted to reduce all these flaps. I don't know, we measured the past. I think there's sometimes you get even up to a few hundreds of updates for a single prefix if you don't do anything at all. So, this is the operator community. We don't have to say a lot here. And therefore, there's the RFD implemented that, if you flap a lot, you get hold back of the announcement, so you don't damage the rest of the world, and your ripple off effect is stopped. This all looks fine, except that when people did the measurement, both by the academics and you people observed in the reality, things didn't work that well. So this, we digged out this previous talk on the topic. There's a bunch of other talks as well, but this particular one had some very rigorous analysis. Basically shows that, there is this thing called path exploration. When one failure happens, thanks or not thanks to the very rich connectivity across the internet, every router tried so hard to find alternative paths, and it takes a while to get the things settled. And all of these updates are actually going to trigger the dampening. I remember Rodney told me a story a couple of years ago that he had one router flipped just once, down and up, and somewhere far end of the internet, this prefix got damped for like half an hour. And he said, this is not acceptable. I agree with that. And that's probably going to trigger your 3 AM calls. So research, community eagerly dived into the problem to say, hey, we're going to fix it. We're going to reduce the false flat dampening. Bunch of schemes invented, trying to figure out how to do a better job. So we listed the name there, one of them even was ours. But the thing is, after all of these tries, none of them is that super successful. Why? Because it's just hard to do the exact decision to say, okay, now we see 3 updates or 5 updates from a prefix, and this must be flapping, so we're going to just cut it off. It's really depends on where you are and how the connectivity looks. You may get 10 updates, but there isn't flap, but just some transient move or change that caused the path exploration and got you to make a wrong decision. And there's a RAP decision back then, it's almost 5 years, recommended that let's not to do the dampening. Now, that seems to be the final words. So why we come here talk again? Because, we do measurements, and we know that the long, persistent, very high frequency flapping does exist. You can talk numbers anywhere. So the question is that, should we do anything about it or not? How bad it can be. I just have this one number here says that top 50 unstable prefixes generates almost like 10% of total updates. Not only that, you can tolerate a little processing overhead because of those flaps. But these days, there's this thing, real-time communications coming along, and the measurement showed that that affected the routing instability, affected the performance of the real-time applications. Like we caught one publication suggesting that about 50% of SCAP outages, the performance issues, are coupled with BGP dynamics. And also, operators want to do something to make the real-time applications, feel better. And therefore, there's a very aggressive reduction in terms of MRAI timer. Either the values get substantially reduced, otherwise, it's just turn off MRAI completely. I think we have observed the increased number of operators turning off MRAI. As a consequence, updates goes up. So it's not a very happy circle. Now, how do you do better than all the current state of art? We think that you can just look at the problem in a slightly different light. You examine the previous the solutions. Fundamentally, people struggled trying to see how we can precisely identify the flapping prefixes, but then we're going to stop them. And that precise identification has been the challenging. So they tie up identification with the suppression. They think they caught the right one, then they dampen it. And we figured that you cannot do a precise job on the damping side, on the identification side. So can you somehow change your suppression rules to do no damage, just in case you make a mistake? What do we mean by that? Let's look at this picture. One thing we notice that is that there's so many so-called covered prefixes. That is, the shorter prefix exists when people also announce longer prefixes. And not only that, the longer prefixes tend to be the unstable ones compared to the shorter ones. Besides this covered versus covering prefix, there's also kind of alternative paths to an unstable prefix. And very often you find out the alternative path is stabler than your most preferred path, which is flapping back and forth. So to give you a illustration of our ideas, this was we think about different sub prefix groups. You think about the whole square I showed up there. It's like a total prefix space. Then the red circle is really the set of unstable prefixes. I said the picture wasn't drawn to scale. Hopefully we didn't really have that big percentage of the unstable prefixes. This is just for the illustration. And then the yellow circle represents whatever the best algorithm you can use to identify those unstable ones. And you can see that they are not really overlapping. With whatever the best thing you want to do, there are always unstable prefixes, so maybe you missed. That is perhaps the smaller percentage. But you can see this overlapping area between the red and yellow. There's a large percentage identified by the yellow. The false identification is not really right. And those are the areas that's potentially, if you do dampening, and you really damaged the good prefix that shouldn't have been damped, and they lost reachability. The blue circle is the thing we identified. We say that, look guys, there are so many prefixes out there. They either have alternative paths, otherwise they have a more stable covering prefix. So what if, given that we cannot do the best identification of unstable prefixes, can we just damping those? That is the overlap between the yellow and the blue. Okay, when we do that, we can guarantee, in case we get it wrong, that would be the overlap between the yellow and the blue, but outside the red area. We don't really do much damage. The reachability is number one, and we are sure that. That's the thought. Now, the question is, what's that percentage, right? It's effective dampening, and you don't lose reachability. So we look at the two situations. One is the unstable prefixes that may have covering prefix. The other is that a prefix have alternative paths. So this really look at all the prefixes. The left figure shows that for all the prefixes, about half of them do not have common prefixes. And then there's like because the CDF, about over 40% has one common prefix, and the more have, there's another point, the two, that's how many they have the two common prefixes. The red figure tells that because you have multiple providers, say you are a customer, and then depending on how many providers you have, essentially each of them can give you a reachability to a given destination. How do we get the number? I have to say that this kind of estimated. We got this one BGP data collector at a London exchange, and we assume that the monitors, the real routers feeding this collector, assuming they are the providers because they give us the full table, and we take the 10 of them, and this is the current estimate. We later played with different games. I don't have it shown here, but at the end of the talk, I have a pointer to a paper we published that tells you that, say that if you only have two providers, you essentially get more or less the same benefit. So now you know that there's a great chance unstable prefix, your so-called identified unstable prefix, which may be true, may be false. There's a great chance there's alternative ways to get to that destination. So what we do now is that take the best RFD scheme that has the highest accuracy in identifying unstable prefixes. This is somebody else's job. We'll take whatever solution other people developed. All we have done is to add this reachability check before you do the suppression. What you do is you get this prefix, you see that does this have an alternative path? We call it protected path. If so, you can dampen it. But then you have to think about the worst case. Say that you have a prefix, longer one, /24 covered by another /20. You say, okay, this is /24 seems to be flapping. Let's stop announcing it because there is a /20 covering it. But prepare for the worst case. What if this /20 is withdrawn? So in that case, then we'll decide to release this so-considered unstable prefixes because our goal is reachability first. We don't want to just sacrifice reachability because it may generate some small number of more updates. Then so that's the basic idea. Very simple. We don't do identification of unstable prefixes. We just say that when you do the suppression, before you do that, do a little check. And for those identified unstable prefixes, if they don't have a protector routes, don't suppress them. That's all we do. And here's the evaluation. Again, we don't really have the real routers to try it out. So what we did was that, using the data collected by the BGP data collector and assuming there's a few feeds, we assume they're the providers to the customers, and let's try it out. So we get the data, the input to the collector, we run them through a kind of a simulated RFD scheme. Because we don't know exactly which one is the best one, we just pick the vanilla one, using the Cisco parameters. We picked the 1 week of data, December 2009, and get 4 peers to this 4 monitors that feed into this collector, and simulating this kind of provider-customer relations. And so basically, we'll measure about reachability loss. We said it's okay because we just as long as the routing table anywhere has a reachability to a prefix, we have it based on our scheme. So what we gain and what we lost is the following. That is, the router load gets reduced because we do dump those unstable prefixes identified. We are dumping those that has alternative paths, and so the stability also gets higher. The router preference sometimes gets sacrificed because, you know, the unstable ones going through provider 1 and the stable ones going through provider 2. If you have preference for provider 1, then, you know, for the time when this path is unstable, you use your less preferred provider. That's the cost. So to illustrate the specifics, let me show you here. You know, say that one customer has 2 providers, and the one is stabler than the other, but the top left line indicating this less preferred but the more stable provider. The lower line on the left is the, you know, announcement and the withdrawals for the preferred provider. If you apply our scheme, look at the red figure. What you got is the top one. That decides that, okay, as far as the reachability is concerned, you do as well as without RFD. As far as the routing changes is concerned, you can see that little triangles represent every routing change. You can see that the first line actually is no dampening, and the last line is our result. The middle line is the vanilla RFD. So you see the bottom line has fewer route changes, and the reachability is as high as without the dampening. And here is a more clear picture on the reachability preservation. If you do vanilla dampening, the bottom line shows, you know, what's the reachability losses. We give some rough percentage there, like 3% of the prefixes that got damped during that week lost the reachability for 10 minutes. And I think the top ones lost for several hours. But if you do our scheme, this slightly different version, the reachability guard versus, you know, reachability guard together with early release, they more or less burn up the reachability to, you know, the total 100%. And also, your router load will be reduced. This is the updates reduction. The rightmost line represents no dampening. That's how many updates you may get. And then the R scheme give you a result more or less, you know, close to you do vanilla dampening. So in terms of the updates reduction, we do almost as good. And only a little more than the vanilla dampening in terms of number of updates. But if you look at the number of next hop routing changes, then we do substantially better than the vanilla dampening. So again, the right, I have to figure out, the rightmost line represents if you don't have the dampening, that's how many prefixes, how many routing changes you're going to have. Then if you do the dampening, that's the leftmost line. And we are more or less overlaps with the vanilla RFD, you know, with a little variation that's slightly departed from that. Essentially, we're seeing that, you know, you don't have reachability losses, but you get almost the same gain in terms of the updates reduction. And then also you gain in terms of routing reachability compared to no dampening. So it's really kind of most of women's situation. The one cost you pay, like I mentioned earlier, is about route preference. If your less preferred provider has a stable path, you may, you know, get onto that path for some time period when your most preferred ones was going through this kind of flapping situation. So this result is based on this one sample points we got from the London exchange points. To verify whether it's really representative results, we look at a number of other data points. So I think that here is the table showing the data collected from other collectors. You can see that the number more or less close. There are some little variations. But the point I want to make is that, for one, we guarantee you the reachability as long as the routing table gives you. And second is that the reduction is really is worth doing. This is the percentage of the total number of updates you received. You think about, would you like your router get a quarter or 1/5 less routing updates? I think that's a great gain. And also in terms of the route stability, we also improved significantly. And then the real-time applications, I think, are going to like that. So to summarize, it's a very simple scheme to guarantee the reachability, and yet we get almost very close to the vanilla RFD reduction in terms of the routing updates. We offer really a much better trade-off between whether you just turn on RFD versus whether you turn off RFD. Okay, because turn on, you may have the loss of reachability. You turn off, you suffer from routing instability and also, increase the router load. Not only that, like I said, we don't really do the instability prefix identification. Whatever the greatest scheme you have, use it. We just add a little checking when you decide to do suppression. So I want to make it very clear about that. We are not just developing yet another brand new RFD scheme. This was very often the first question people say, oh, just another RFD. And I want to tell you, no. We just do a patch for whatever your favorite RFD, if you have one, to make it guarantee reachability of the prefixes being down that seem to be unstable. And this, academically speaking, of course, we only talked about the gains. There's a little loss in terms of preference, but there's a bigger concern, that is how easy this would be to really implement. That is a question for other people to answer. So for more details, I put on there the pointer to a paper we actually presented last year at some conference that gets you a lot more data and a more detailed description.
Hi, Alicia. Jeff Oz. So I think this is implementable. I think having these numbers is a really good thing. You've been wanting this sort of thing for a while. The one question I have that might be in your numbers but not talked about in your slides is, for these more specific covered prefixes, have you done the fate sharing analysis to see, are these more specifics actually within the same network as the less specific?
No, we haven't done that one.
So one of the things I'd suggest as a follow-on to this paper, which is really important, it's often the case that these more specifics are, being leaked out for traffic engineering purposes or other things.
We identified those cases, yeah.
But it's also the case that occasionally customers will wander away with a portion of your address space and live elsewhere on the network, and unfortunately suppressing that more specific in the case where the less specific network isn't providing transit to it anymore can cause them problems. So it'd be interesting to see that explored further in your work.
Thank you. We'll do that. We did catch the places where, you mentioned about traffic engineering. It's very clear. They just, do that. But we need to do a more quantitative measurement to answer your question. Yeah.
Kayur Patel, Cisco. Just a quick note to follow up on the Jeff's comments. If you end up suppressing more specifics, in that case, you won't be any worse than the existing route flap dampening cases that you have today. So.
No more questions? Thank you.